Assalamualaikum and very good morning. Okay, next we are going to discuss on the other antenna fundamentals, antenna efficiency. So it basically represents how effective the antenna deliver the electromagnetic wave out of the antenna structure from the input source. Okay, mathematically the antenna efficiency is defined as the ratio of power radiated by the antenna to the power supplied to the antenna. Okay, lower efficiency antenna may indicate that most of the power at the input terminals is absorbed as losses or radiated back or reflected back due to the impedance mismatch. And higher efficiency antenna may indicate that most of the power at the input terminals of the antenna is radiated away from the antenna. Okay, so the total antenna efficiency can be represented by this equation. E0 is the total antenna efficiency considering the losses at the input terminals and within the antenna structure itself. So the losses at the input terminals and within the antenna structure may be due to reflection when there's mismatch between the transmission line and the antenna structure, and also may be due to conduction and electric losses. Okay, so the total antenna efficiency E0 is basically the multiplication between ER and ECD. So ER is the reflection mismatch efficiency defined by 1 minus gamma squared, and gamma is the voltage reflection coefficient at the input terminals of the antenna. And while EC and ED, EC is the conduction efficiency and ED is the electric efficiency. So the equation may be simplified as ER multiplied with ECD, and this ECD is the antenna radiation efficiency. So in this case, the total antenna efficiency is the multiplication between the reflection mismatch ER multiplied with radiation efficiency ECD. And ECD is basically difficult to compute. However, it can be determined through experiment. Okay, and the total antenna efficiency E0 may be simplified as ECD 1 minus gamma squared, in which 1 minus gamma squared represent the ER reflection mismatch efficiency. Okay, next let's discuss on the gain. So gain is one of the parameters that used to indicate the antenna performance. Right, so the gain basically defined as the ratio of the radiation intensity in a given direction to the radiation intensity U when the power accepted by the antenna were radiated isotropically. Okay, if you refer to this figure, the gain basically indicates how strong the signal will be directed to the intended direction. Okay, meaning that it's related to the directivity of the antenna and also the efficiency of the antenna. Okay, the higher the gain, theoretically the higher the gain, the farther the the signal will be traveling in the intended direction. Okay, if you refer back to the equation, so it's related to the radiation intensity. If you still remember that the radiation intensity for isotropic source is given by P rad, radiated power divided by 4 pi. So in this case, the gain is the ratio between the radiation intensity in the maximum direction to the radiation intensity when the power accepted by the antenna were radiated isotropically. So in this case, the power accepted by the antenna, meaning that the power at the input point of the antenna, okay, were radiated isotropically. So the we can relate the radiation intensity at this point, at the input point, equal to P radiated power, or in this case the accepted power, equal to P in divided by 4 pi. Therefore, the gain equation may be simplified to 4 pi multiplied by U, the radiation intensity in the intended direction, divided by P in, the accepted power to the antenna. And the relative gain is the ratio between the power gain in a given direction to the power gain of reference antenna in its reference direction. Okay, usually dipole antenna and horn antenna is used or are used as the reference antenna, or other types of antenna can be used as well, as long as the gain of the antenna can be calculated or can be is known, or the gain of the antenna is known. Right, so the relative gain is given by G equal to 4 pi U, and in this case the reference antenna is the P in for the reference antenna. And in most of the cases, the reference antenna is assumed to be a lossless isotropic source. And the total power radiated is different to the input power, okay, in which the radiated power is equal to ECD multiplied by P in. So ECD is the radiation efficiency of the antenna. In this equation, the antenna transmission line connection loss, or the reflection mismatch loss, ER, is not included. Okay, in this course we are going to discuss two types of gain, which are the gain in which the reflection or mismatch loss are not considered. So mismatch loss in between the transmission line to the antenna is not considered. And another one is the absolute gain, in which the reflection and mismatch loss has been considered in the equation or in the calculation. So for gain, where there's no reflection or mismatch loss included in, so the gain related to the maximum directivity is given by G, the gain equal to the antenna radiation efficiency multiplied by the directivity. So for maximum gain, G naught is equal to the radiation efficiency multiplied by maximum directivity, or the equation can be simplified to ECD multiplied by D naught, or the maximum directivity. While for the absolute gain, it's more or less the same equation. However, in this case, the reflection mismatch is considered ER. Alright, so if you still remember, the total efficiency is equal to ER multiplied by ECD. So for gain, only ECD is considered, and for absolute gain, the ER and ECD, both ER and ECD are considered in the equation or in the calculation. So in this case, the absolute gain is equal to ER multiplied by ECD, or in this case it is E naught, the total efficiency, multiplied by the directivity. And the maximum absolute gain equal to G naught absolute is equal to E naught, in which it is equal to ER multiplied by ECD multiplied by the maximum directivity. So the absolute gain can be simplified to E naught multiplied with D naught. Okay, in case of the antenna is matched to the transmission line, the antenna input impedance is equal to the characteristic impedance, like C. Therefore, the two gains are equal, G equal to G absolute. So we will be discussing on the VSWR related to the input impedance later on. Okay, in many practical antennas, the total gain can be approximated, in which the total gain is equal to G naught equal to G theta plus G phi, in which is the sum of the partial gain for any two orthogonal polarization. Okay, so we are going to discuss the polarization later on. So the component or the partial gain of G theta and G phi are given by the following equations, in which the G theta equal to 4 pi U in theta polarization divided by 4 P in the accepted power, while G phi is the equal to 4 pi U the radiation intensity in phi polarization direction divided by P in the power accepted by the antenna. Okay, so the U theta is, as mentioned, is the radiation intensity in theta direction, and U phi is the radiation intensity in phi direction, or E phi component, and P in is the total input power accepted by the antenna. Alright, so the total gain of the antenna can be approximated by using this equation, in which G naught is equal to 30,000 divided by theta 1D multiplied by theta 2D. And in dB, okay, usually the gain of the antenna will be presented in dB. So you can convert the linear value into dB, which given by 10 log 10 of ECD multiplied by the maximum directivity. And this figure shows the gain pattern relative to the isotropic or the reference pattern, and also the dipole antenna radiation pattern. Okay, next is bandwidth. So bandwidth is defined as the range of frequencies within which the performance of the antenna conforms to a parameter specification. Okay, parameter specification such as VSWR, gain, radiation pattern, and etc. Okay, VSWR and VSWR is commonly adopted in bandwidth measurement, and VSWR will be represented as a ratio, for example 2:1, which means that the range of frequencies when the VSWR is less than 2 will be chosen in bandwidth calculation. Okay, so for example, we can measure the bandwidth by referring to the return loss or S11 graph, and also the VSWR graph. For example, in the return loss graph, it will be measured at minus 10 dB line. So you will draw a minus 10 dB lines. Okay, so in this case, the maximum frequency, okay, surrounding the targeted or resonant frequency of the antenna, and also the minimum frequency that lies within the 10 dB range will be chosen in order to calculate the bandwidth. So in this case, for example, the F2, we call this F2. So F2 is around here, and F1 is around here, and don't forget to look at the unit, in this case gigahertz. So the bandwidth is equal to F2 minus F1. So for a VSWR graph, if the ratio stated is 2 to 1, so we will be looking at the frequency lies when the VSWR is less than 2. So we draw a line at 2. So we'll measure the F2 and F1 as well. So in this case, the bandwidth is equal to F2 minus F1. So in this case, F2 is around, it's 2.67, maybe 2.67 gigahertz, minus F1 is around 3.38 gigahertz. So you'll get 2.67 minus 2.38 gig. So it's around 290 megahertz. Okay, so it's around 0.29 gigahertz or 290 megahertz. Okay, so another commonly used way to specify bandwidth is percentage bandwidth, which you need the information of the center frequency value. So let's look at the example of this VSWR graph. So the center frequency, we assume it is here. You can say F0 or FC. So in this case, the percentage of bandwidth is equal to F2 minus F1 divided by the center frequency times 100%. So in this case, F2 is 2.67 minus 2.38 divided by, we assume the F0 is equal to 0.5 here, gigahertz, multiplied by 100%. So you'll get the bandwidth is around 11%. Okay, for broadband antenna or wideband antenna, the bandwidth is usually expressed as the ratio of the upper to lower frequency of acceptable operation. For example, if the bandwidth stated is 10 to 1, so this will indicate that the upper frequency is 10 times larger than the lower frequency. Okay, and please take note, this is for bandwidth. This is not the VSWR ratio. For narrowband antenna, so the bandwidth is expressed as the percentage of frequency upper minus lower over the center frequency of the bandwidth. Okay, this is the percentage bandwidth that we have discussed earlier. Okay, for example, if the bandwidth given is 5%, this will indicate that the difference of acceptable operation is 5% of the center frequency. Okay, so the center frequency of the bandwidth, for example, from the previous slides, is 2.5. So 5% from the center frequency. Okay, the figure shows the comparison between the narrowband and wideband. So the red lines indicate the narrowband. When you refer to, this is the return loss S11 graph. So when you refer to minus 10 dB line. Okay, so this is the bandwidth for the red line, so we call bandwidth for red line, and the other one is bandwidth for the blue lines, the blue graph. So we can see that the bandwidth for the blue lines is larger than the red lines. Okay, so this shows the comparison between the wideband to narrowband antenna design. Okay, and the antenna usually will be designed depending on the targeted application. So some application requires larger bandwidth, and some may works by using narrow bandwidth. Okay, next is VSWR, voltage standing wave ratio, which is an indication of the amount of mismatch between an antenna and the feed line connected to it. Okay, so when there's a source, the power transferred from the source into the transmission line towards the load. Okay, when there's mismatch, meaning that when the impedance load is not matched to the transmission line, so not all the power transferred will be transferred to the load, so it will travel back and forth within the transmission line towards the source. So this will create a standing wave. Okay, standing wave. So the ratio between the maximum, the peak voltage, and the minimum peak minimum voltage will determine the voltage standing wave ratio. Okay, the VSWR range from 1 to infinity. Okay, a good match antenna can be determined when the VSWR value is under 2. Okay, usually the common VSWR will be less than 2, from 1.5 to 2, and when the VSWR is higher than 2, the antenna is considered poorly matched. Okay, for example, typical value for VSWR would be 1.5 to 1. So the VSWR will be presented in ratio. So the first part of the ratio basically tells the impedance mismatch against perfect impedance match, while one at the back represents the perfect match design. Okay, as shown earlier, we can see a sample of VSWR graph. So we can determine the bandwidth for the VSWR graph. Okay, and by referring to it, we assume that the VSWR is 2 to 1 in this case. So the bandwidth can be measured by considering the F2, the maximum frequency, when the VSWR is 2 or less than 2. Okay, let's look at an example on the topic that we have discussed so far. So given a lossless resonant half wavelength is lambda over 2 dipole antenna with input impedance of 73 ohm. So in this case, input impedance is Zin equal to 73 ohm, connected to a transmission line whose characteristic impedance is 50 ohm. So characteristic impedance is Z0 equal to 50 ohm. Assuming that the pattern of the antenna is given approximately by this equation, U is the radiation intensity, determine the maximum absolute gain, so G abs max, or we can say G0 absolute of the antenna. Okay, so in order to solve this, you need to have the equation for absolute gain in hand. So G absolute maximum is given by E naught D naught. D naught is the maximum directivity and E naught is the total efficiency. Alright, so let's revise back. The E naught is the total efficiency is equal to ER ECD. So ER is the reflection mismatch while ECD is the radiation efficiency. So in this case, since it is mentioned the antenna is a lossless antenna, so meaning that the antenna is completely efficient, so the radiation efficiency ECD is 100% or equal to 1. So in this case, E naught equal to ER multiplied by 1. Okay, so E naught equal to ER in this particular case. So what is ER? ER is the mismatch, reflection mismatch. So ER is given by this equation, 1 minus reflection coefficient or the gamma squared. So for gamma equation, so the reflection coefficient, the gamma or reflection equation, reflection coefficient equal to Z in minus Z naught, the characteristic impedance divided by Z in plus Z naught. So in this case, the Z in given is 73 minus Z naught, characteristic impedance equal to 50 divided by Z in 73 plus 50. So in this case, the gamma or the reflection coefficient equal to 0.187. Okay, so from here you can calculate the E naught. Okay, sorry, this is E naught, in which E naught equal to ER in this case. So next is E naught equal to 1 minus gamma squared. It is equal to 1 minus 0.187 squared. So E naught equal to 0.965. So the total efficiency of this particular antenna is 0.965. Okay, so G absolute just now, G absolute equal to E naught, D naught. So we have calculated the E naught. It is equal to 0.965, 0.965 multiplied by D naught. So now we need to figure out what is D naught. So D naught is the maximum directivity from last week's slides. So D naught is equal to 4 pi multiplied by U max, the maximum direction, divided by the radiated power. Okay, let's determine what is your U max. So given from the question that given U is equal to V naught sine cube theta. Okay, so in this case, U equal to V naught sine cube theta. So U max is happening when the sine theta, when theta equal to 90 degree. Okay, so in this case, U max equal to B naught. Okay, so we have determined this. Now we need to calculate P radiated or radiated power. So P, the radiated power. Okay, let's revise back the equation for radiated power is equal to U d ohm. The integration of U d ohm, in which it is equal to U d ohm is sine theta d theta dV. So the integration from theta equal to 0 until pi, and the phi is from 0 until 2 pi. So now your radiated power equal to U is equal to B naught sine cube theta. So it's B naught sine cube theta multiplied by sine theta d theta dV. So integrate them over theta and also phi. So this one will reduce to this one until 2 pi, and this one until pi. 2 pi B naught, the integration of theta from 0 until pi, so sine to the power of 4 theta d theta. Okay, so you solve the integration, then finally you'll get P rad equal to B naught 3 pi squared divided by 4. Okay, so now you can finalize what is your D naught. So in this case, your D naught is equal to 4 pi. So your U max equal to B naught divided by P rad. P rad equal to B naught 3 pi squared over 4. So your D naught in this case is equal to 16 over 3 pi, which is equivalent to 1.697. Okay, so we have had the E naught and D naught, so you can calculate the G abs. Absolute gain equal to E naught D naught equal to 0.965 for your E naught, or the total efficiency, and the maximum directivity is 1.697. So your G abs is equal to 1.6376. So in dB, G abs in dB is equal to 10 log 10 of your G abs. So it is equal to 10 log of 1.6376. So your G abs will be around 2.14 dB. Okay, please recalculate this. There may be a careless mistake, so please recheck again. So G absolute for this particular antenna is equal to 2.14 dB. Alright, with that I end this session. Thank you.